All right, so today we are going to talk about substitution rule. The idea is to compute integral f of x dx, which is a definite integral, indefinite integral or antiderivative. And or the definite integral, say f of x dx, a to b, right? Now, a motivating problem, for example, could be, suppose I want to integrate e to the power 2x plus 1 dx. Yeah, so let's consider this indefinite integral. Now, generally, so we know using our antiderivative tables or early antiderivative exploration that integral of e to the power x dx is e to the power x plus c, the constant of integration. Question is, how do we integrate here e to the power 2x plus 1, where you can see clearly that it's not really just e to the power x, but 2x plus 1. Yeah. So how do we go about it? Yeah. So the way here is using substitution. So we have the following. So what we can do is let 2x plus 1 du. And in that case, we get, this will give us, take derivative on both sides. So we get 2. So take du by dx on both sides. So we get 2 equals to du by dx. And this gives 2x or 2 dx equals to du, or you can see that it will give us dx equals to du over 2. Yeah. So this comes from the idea of differential, right? Yeah. So so what we have done is we have done substitution here, and in this substitution, so this integral, let me just call this I for a second here. So I is going to be e to the power u. So I've replaced now this by u, and then dx will get replaced by du by 2. Right. So, and we can bring out the half e to the power u du. So now we can integrate this, right? Because this is similar to, is exactly this integral here, right? So we get, this is equal to half e to the power u plus c. And then we get half. Now we should put back what our u was. So u was 2x plus 1. So we get, so this process of integration is called integration by substitution. Okay, so it helps us compute slightly more complicated integrals than just the basic antiderivatives, right? Let's look at a few more examples. So, for example, let's take again another example. Where we have integration of x cubed cosine of x to the power 4 plus 2. So now when I look at this problem, I see that this is not antiderivative of any known function right away, at least not in the one of those we have seen in the table, right? So when I look at this problem, I'm thinking, so there are many techniques to do the integration. And one of the techniques is basically you're trying to see, hey, the integration, so the derivative of this, which is 4x cubed. So which is x cube up to a constant multiplication, is here. Yeah. So in that case, we say, okay, let u be x to the power 4 plus 2. So we do this substitution, and then we get this implies that du by dx is going to be 4 x cubed. So now you see that we have found out substitution for this guy here, x to the power 4 plus 2, and we have also found out substitution for x cubed dx, which is going to be, so this gives us du by 4 equals to x cubed dx. Now let's put back everything here. We get, so I'm going to replace x cubed dx with du by 4, and this is going to be cos of u. Right, now we can take 1 by 4 out, and integration of cosine is, or antiderivative of cosine is sine, so sine u plus c. And then we have to substitute back what our u is. So our u is x to the power 4 plus 2. So this is how the substitution rule works. Okay, let's look at another problem now. Integral of x 1 plus x squared. Yeah, so far I'm only tackling, as you can see, I'm only tackling indefinite integral. We'll see later soon how to see this process in terms of definite integral as well. So again, when I look at this problem, there's no basic antiderivative for x upon 1 plus x squared. So now you ask the question, oh, do I have, so let's see, 1 plus x squared, if I take that to be u, the derivative of that is 2x, which is on the top, right? So again, so let's say, let's do the following. So let's do the substitution. Let 1 plus x squared u, and this gives me 2x dx equals to du. So now I found out substitution for this, which is going to be u. And now I'm going to replace. So the idea is once I do the substitution, everything should be in terms of the variable u. So this becomes x dx is by, and therefore I can now replace this integral. Let's call this I. I is going to be, now instead of denominator 1 plus x squared, I'll have u. Instead of x dx, I'll have du by 2, which can be written as du by 2. I can bring 1 by 2 outside. Integration of du by u, which is integration of 1 by u is ln u. This is going to be ln of absolute value of u plus c. And then once you have that, you can substitute back what your u is. So you get ln of x squared plus 1 plus c, because your u is 1 plus x squared. Now let's look at another example. So we have, say, integration of tan x dx. So again, we do not have elementary antiderivative for tan x. We don't have any function right away. I mean, at least from the basic list, we cannot find out the integration of tan x. Okay. But notice the following: we can see that tan x is can be written as sin x over cosine x. Right? And the other thing to notice is that the derivative of cos x is on the top. So we have derivative of cos x is minus sin x. So we can do the substitution now. So again, the same story. let u be cosine x, then we get du by dx equals to minus sine x. And this gives me, so now I'm going to replace cosine x by, u, and sine x dx. So we need a replacement for that. So let's see, we get du equals to, or minus du equals to sine x dx. Okay. So now we can replace the whole thing, the whole expression. So on top, instead of sine x dx, I'm going to write du, but with a minus sign, which I can leave outside. And then in that case, I get, this is going to be minus ln of u plus c. And now let's substitute back what your u is. So we get minus ln of cos x plus c. Okay, so this is how this works. Okay, so let's look at another example now. Say we have x squared plus, so x squared divided by square root of 1 plus x dx. Now let's try to basically let's try to compute this. The integration of x squared upon square root of 1 plus x. Now, as you can see, we cannot simplify this further, right? I mean, we cannot use any of the elementary, again, the list of antiderivative formulas we have. So let's try the following substitution. So what we'll do is, in this case, we'll say let u be 1 plus. And in that case, we get du equals to dx. And you will get, so from here, we also get that, we also get u minus 1 equals to x. This implies that u minus 1 square equals to, now the integral becomes u minus 1 square on the top, and the bottom square root of u. Then we have dx the same as du. And now we can expand it out. So we get u square minus 2u plus 1 divided by square root of u. And this can be seen as, now you can distribute the square root of u throughout here. So we get u to the power 3 by 2, u to the power square root of 2, plus u to the power minus half. And I can also write this as power right away, right? So this is going to be, second term can be also written as u to the power half. Now let's integrate this. So we get u to the power 3 by 2 plus 1, which is 5 by 2. 5 by 2 divided by 5 by 2. Divide by 5 by 2, which is 2 by 5, minus u to the power half plus 1, so u to the power 3 by 2 divided by 3 by 2, which is going to be multiplying by 2 by 3. That's going to be 4 by 3. And then here we have u to the power half plus 1, so u to the power half divided by half, the same as multiplying by 2. See? And then you put back what your x is. So your x is, so u is in terms of x. So we get 2 by 5, 1 plus x to the power 5 by 2, minus 4 by 3, 1 plus x to the power 3 by 2, plus 2 times 1 plus x to the power half, plus 6. Okay. Now here's the question. So, I mean, like in all the other ones, you could see the derivative of the function on the top, I mean, multiplied with du, and that's why you substitute it, right? In this case, one may think, oh, well, so substitution looks slightly artificial. But the answer to that thing is, I mean, you can, as it stands, we cannot integrate it. Yeah. So the idea would be to have denominator as square root of u, which we can distribute later on and do the integration. And that's why we use this technique. All right. So this is the computation involved in doing substitution rule for indefinite integer. Now let's try to calculate. The next thing is let's apply this to calculating, to calculate a definite integral. How would we go about that? Using substitution. So let's look at the example. Say integral 0 to 1 x 1 plus x squared dx. Suppose I want to integrate this. How do I go about it? Well, one way is what we did earlier. We basically first compute. So method 1, for example, would be just to compute the usual antiderivative and then use the FTC too, right? So, well, so let's see. So for example, we could have done this computation without caring about the limits of integration. And in that case, we let, again, I'm going to this problem. We have already done it before, but we let u equals to 1 plus x squared. You got du equals to du by 2 equals to x dx, and then this integral becomes du by 2 u, and then we have half ln of absolute value of u plus 3, and then you get half ln of x squared plus 1. I'm ignoring the absolute value because x squared plus 1 is positive anyway all the time, right? So now I have this. This can be seen as my capital F of x. And then I can say, okay, this integral I, call this I is going to be f of 0, sorry, f of 1 minus f of 0, right? Using FTC2. And then you basically substitute half f of 0, f of 1 is going to be ln of 1 square plus 1. You can ignore the c as we have already discussed. Half ln of 0 square plus 1, which turns out to be half ln 2, and ln 1 is 0, right? So it's half ln 2. Okay, so that is method 1. All right, usual computing the indefinite integral and then connecting with FTC. Now method 2 is similar, but in method 2 we basically change also the limits of integration. So what we do is the following. So we have 0 to 1 again, x 1 plus x squared dx. You are doing the same substitution. Let we have let 1 plus x square be u, then you get same thing, you get x dx equals to du by 2, right? However, the extra piece here is in the method 2 is you also change the limits of integration. What does it mean? See, the values for the limit of integration for the variable x. Now, if you're changing it to u, you should say, well, when x is 0, then we get, then u equals to 1 plus 0 square, which is 1. And when x equals to 1, we have u equals to 1 plus 1 square, which is 2. Okay. So therefore, this limit, sorry, this integral transforms into, now we can change everything in terms of new variable, even the limits of integration. So we have 1 to 2. The inside part is changed as half du by u. Yep. Du by u, not du by u. And then this becomes half ln of absolute value of u. Limits are from 1 to 2. And then we have half ln of 2 minus ln of 1. You can keep this in bracket, and that becomes half ln of 2. Okay. So you get the same answer. I mean, this should not be surprising here and here as well. So the key part is, or the key difference is the following. In method 1, you compute the indefinite integral, you get to the function f, and then you do f of upper limit minus f of lower limit, as in FTC2. In method 2, you're doing the same substitution, but you are also changing the limits of integration right away. Okay. So please note that these two things are, suppose I do not change the limits of integration, then what happens? Let's see. So if I say, okay, 0 to 1, I have 0 to 1, x, 1 plus x squared dx, which we computed. So when we did the substitution, we got half integration of du by u. And if we do not change the limits of integration, suppose I keep 0 to 1, then these two are not equal. Okay, so this is a big step, that if I do not change the limits of integration, these two are not equal, right? Let's check it out, right? Here we got answer to be half ln 2, but if I suppose do this, I will get half ln u, limits are from 0 to 1, and then that becomes half ln 1 minus ln 0, and that ln 0 doesn't even make sense, right? Yeah, so these two are clearly not equal, right? So these two method of computing are not equal. Yeah, and the idea is that this, so you do the either of two things. Again, let's go through it. We have either we compute the indefinite integral, then so we basically convert it into u, compute the indefinite integral, convert it back into x, and then put the limits of integration for the x, like f of upper limit minus f of lower limit, as we did here. Or you can do the following. You can change the, while doing this substitution, you can also change the limits of integration. And in that case, you don't have to convert it back into the variable x. Okay. All right. All right. So a few things here. So let's look at few properties, what this substitution rule gives us. And another word of caution, not every integral can be done using substitution rule as well. Yeah. The key observation is So you have f of g of x, and then you have g prime x dx. If your integral is of this form, what you do is you let u equals to g of x, then you can see du by dx becomes g prime x, and then you have du equals to g prime x dx. So now you're able to substitute this whole thing as integral. It will become f of u, and then instead of g prime x dx, it becomes du. So this integral, of course, these two are not equal. I mean, the idea is they're only equal after computing the integral, you substitute u equals to g of x back. Yeah. So this is how the substitution rule works. Okay. So we will see there are other techniques of not everything fits in this description, right? So we'll study other techniques as well, like say, for example, integration by parts and so on and so forth. But as I said earlier, substitution rule basically works for this kind of setup. All right. Okay. Now let's see few properties what substitution rule gives us, namely, if I have integral a to b f of x dx, then this is same as integral b to a f of x dx, but with a minus sign. Okay. So let's see the proof of this. So proof, yeah. So what is the proof? The proof is here we can use FTC2 again. So recall by FTC2, what do we get? We have the following. So if we have if f prime x equals to f of x, that is same as saying that capital F of x is the antiderivative of the function f of x. Then we have integral a to b f of x dx equals to f of b minus f of a, which can be seen as, bring the minus sign out, we have f of a minus f of b. But again, the inside part can be seen as what can be seen again by FTC, can be seen as integral b. So in this case, we can see integral b to a of f of x. Again, this is the property of FTC2. Okay. So yeah, so if you change the order of, if you change the limit of integration, like by change here, if I mean, if I flip the limit of integration, I just need to put a minus sign in that. All right. Now, another interesting example is computing some integral of odd and even function. Okay. So recall, we computed this integral. Let's look it up anyway. So you have, if we take f of x equals to sine x, let this be f of x equals to sine x from minus pi. So the idea is, if I want to compute integral of minus pi to pi of sine x dx, we've already seen that this area is this integral So if you look at this as a1, or this is a, then this is also a. So this is a minus a equals to 0, right? So sine x is an odd function, and you see that you integrate from minus pi to pi of sine x dx, then it's going to be a minus a and 0. Not only that, if you just take any value, say minus b, if you compute integral of minus b to b of sine x dx, it's always going to be 0. Yeah. So let's generalize this. Sine x is an odd function. So recall, what is an odd function? The odd function. So we have, for odd function, we have f of minus x equals to f of x. What are the few examples we have of odd function? Like all odd powers are odd function, right? So we have x, x cubed, x5, so on and so forth. And also, as we know, sine x is also odd function. Yeah. So when you take an odd function and you integrate from minus b to b, as you can see here, what happens is you'll get one part of you'll get the same area, one with the positive sign and the other one with the negative sign. Okay, so let's prove this. So suppose f of x is an odd function. Then integral minus a to a of f of x dx. Our observation tells us what? That this integral will be 0. So let's see, is our observation true? So is it 0? And to see this, we will use substitution. So let's say, so we call this as result, okay, or theorem if you want to call it. So let's see. So how do we go about it? So let's break this integral minus a to a f of x dx can be seen as minus a to 0 f of x dx plus 0 to a f of x dx. Yeah. So what is an odd function? F of minus x equals to minus f of x. So now I have this. So now I'm going to convert this integral. Let's see, how do we basically, so I'm going to do a substitution here. So let x be equal to minus u. Okay. So in that case, we get dx equals to minus du. And let's change the limit of integration as well. When x equals to, so let in integral 1, okay? Let's label this as 1, and let's label this as 2. We don't want to change 2, we want to change 1. Let's see. So we get dx equals to minus u. So we get now when x is minus a, this will give me u equals to a. And when x is 0, this will give me u equals to 0. So now my 1, integral 1 transforms to f of u, sorry, f of minus u. And what do I have? In this case, the lower limit now is a to 0. And instead of du, I'm going to write what? Instead of dx, I'm going to write minus du. So du minus. And then the second integral I'm going to write as it is. Again, as you can see where this game is going, here, remember, we from minus b to 0 is negative of the this area a, we have it with the minus sign, and this area A we have with the plus sign here, right? So that's what we are trying to do here. So we are going to show that one is negative of the other. So let's see. So this will become A to 0. So f is an odd function. So f of minus u is minus f of u. That minus and this minus will cancel out each other. We have f of u du. And now you have A to 0. You can write it as 0 to A, but with the minus sign as seen by the property we did earlier. And now you have u. You can actually replace it by x, because now in this case it becomes a dummy variable. Okay, this integration is going to be the same. So we can say minus 0 to A f of x dx. So 0 to A f of x dx. And then when you add them, you get basically, essentially you get 0. So if f of minus x is same as f of x, then f is an even function, right? So now in that case, what happens to the integral minus a to a of f of x dx? So let's look at an example of a function which is an even function. So let me just look at few examples of even function. Say f of x equals to x squared, x to the power 4, all the even powers, and also there are other examples like cosine x, right? Yeah. Oh, and there are other examples as well, x squared upon 1 plus x squared, for example, right? So these are examples of even function, that f of minus x is same as f of x. Now let's look at pictorially what happens. Let's take x squared. So let this be minus a, and we want to find out the integral of this. So this is a, this is a. It seems that even functions are symmetric around y-axis. So you can see that integral minus a to a f of x dx seems to be that it is same as integral, it is a plus a, which is 2a, which is same as 2 times integral 0 to a of f of x dx. Yeah. So this is what it looks like from the diagram, and it is indeed true. Yeah, we can show this quickly. So I'm gonna just outline the proof here. And what do I want to say? I want to say following theorem or result. So if f is an even function, then we get integral a to a f of x dx is twice 0 to a f of x dx. Okay, and the proof lies the same. The proof idea is precisely similar as substituting x equals to minus u and working it out. Okay, so again you break this. So let me just give you the hint. So we take the left hand side and break it as 2 integral 0 to minus a to 0 f of x dx, then 0 to a of f of x dx, and then you basically in this integral you let u equals to minus x and then work it out. Yeah, in the end you'll get both the integrals are same, and that will prove that you're actually adding twice of integral 0 to a of f of x dx. Okay.